Hi, my name is Holfester. I'm a graduate student at the University of Chicago, and this poster summarizes some recent work that I've done understanding what constraints non-invertible symmetry can place on a quantum field theory. The motivation for this work is that two very standard applications of conventional symmetry in QFT is to explain and predict the presence of degenerate mass states in the theory, as well as to understand the vanishing of S-matrix elements. Both of these are, of course, well understood using the language of representation theory of groups. Now, it's been advocated since the now classic 2014 paper of Gaiotto, Kapustin, Seiberg, and Willett that the notion of symmetry in QFT should really be taken to be synonymous with the existence of topological defects in the theory. And if we take this perspective seriously, we should then ask what kind of constraints such so-called categorical symmetries can place on particle degeneracies and S-matrix elements of your theory. Together with my collaborators, I've fully answered this question for finite symmetries of bosonic QFTs in 1+1 dimension. In this poster, I outline the appropriate notion of how categorical symmetries act on states in this setting, and how to understand their associated representation theory. I also sketch an application of using these techniques to simply understand observed degeneracies in a model that has long defied a standard group theoretic explanation. In a bit more detail, the basic algebraic data that describes a finite symmetry of bosonic QFT in 1+1D is a pair consisting of something called a fusion category and an associated module category. A fusion category is an algebraic gadget that essentially describes the topological defect lines of your theory along with their topological junctions, while a module category is a gadget that describes how the defect lines interact with the boundary conditions of the theory. Given this data, we identify how line defects should be understood as acting on states in the Hilbert space of the theory, with the actual action of the categorical symmetry on states being through an algebra that we call the strip algebra, which is defined given the data of a fusion category and an associated module category. The strip algebra turns out to have many nice properties, which can be concisely summarized by saying that it's a C-star weak Hopf algebra. The weak Hopf part of this means that its representations admit a notion of tensor product, and therefore an action on multi-particle states, and also a dual, or what you might call a charge conjugate. While the C-star part means that the algebra is also compatible with the inner product of the Hilbert space in an appropriate sense. So together, this means that the algebra can be used to constrain multi-particle scattering. Now, as a result of these properties, the representation theory of the strip algebra is very studyable and it's essentially a natural generalization of the unitary representation theory of finite groups. Moreover, it emits a very simple description using the tools of 2+1D topological quantum field theory. This being through a mild generalization of what people often call the symmetry topological field theory, to the case where the QFT has a boundary condition and one studies its boundary changing operators as well. The essential punchline of our work is that the actions of finite categorical symmetries in 1+1D replaces the representation theory of groups with the representation theory of weak Hopf algebras, and that it's really this representation theory that governs the existence of particle degeneracies and the vanishing of S-matrix elements, with an especially novel aspect of the categorical symmetry in this context being that it's also able to enforce degeneracies between particle-like and soliton-like excitations. Given that categorical symmetry is so ubiquitous in 1+1D QFT, this work offers potential for new insights in constraining particle content and dynamics of 1+1D systems, and also serves as a foundation for studying constraints of categorical symmetries in higher dimension.